Yeah, so create a simple triangle that has a dot in the middle of the triangle.
So what about this one?
Okay.
This one has a dot in the middle.
Fascinating.
And a dot on the edge.
Okay, so how many dots does this triangle have on its edge?
It has one dot on the edge.
And one dot.
Well, technically, if you're looking at all of the dots, then it's 4 on the edge and 1 in the middle.
Okay, and why would we want to look at all of the dots?
For our formula.
Okay, so this has 4 on the edge and 1 in the middle. What happened when you had 4 on the edge and none in the middle? What was the area?
The area was 1. I think.
1, okay. What's the area of this triangle?
Well,
It's the base of 2, height of 2,
so
2.
2.
Ah, so we added a dot in the middle, and what happened to the area?
The area increased by 1.
The area increased by 1. All right, let's see if we can find another triangle that has exactly 1 dot in the interior.
It could.
Well, this wouldn't have any dots in the interior.
Okay.
But if you moved it to here, I think this dot's on the interior.
Aha. Okay.
This
And
is
what's the area of this
base
triangle?
of 2, height of 2, still 2.
Interesting.
Seems like maybe all of the ones that have a dot in the middle have an area of 2. But what if you... What if you have more than one dot in the middle?
Okay, this is an interesting example here. How many dots does this triangle have on its perimeter?
Well, it has 1, 2, 3, 4, 5, 6
Okay.
dots.
So what should its area have been?
I think it was 2.
2. So 6 dots with no dot in the middle. We should have found an area of 2. Instead, what is the area of this?
Oh, it's...
It would be 3.
Because you have a base of 2.
Height of 3.
And what's special about this triangle?
There's a dot in the middle.
There's a dot in the middle. So what seems to be happening when we add a dot in the middle?
The dots in the middle increase the area by 1.
Aha.
Interesting.
Interesting. So what do you suspect? We're gonna kind of stop it here, just because we've gone for a long time on this project.
Well,
What do you suspect is the formula for the area of a triangle on a grid?
so it should be
maybe it would be the dots on the edge.
the dots. It'll be the dots on the edge. It'll be the dots on the edge times a half.
Divided by 2.
So okay, so dots on the edge divided by 2.
And then plus the number of dots you have in the middle.
Okay, that's not quite the formula you had before.
Well, we had it in -2.
Where?
So dots on the edge -2.
Right.
Dots on the edge minus 2.
Divided by 2.
I'll call those edge dots just to save space. Divided by 2 plus dots in the middle. Because remember, your simple 1 by 1 right triangle had 3 dots on the edge, and its area was a half. So you got to do that minus 2 there.
Yep.
So edge dots minus 2 divided by 2 plus dots in the middle.
I guess you have to put parentheses around that.
Good. Yeah. Good point. Edge dots minus 2 over 2 plus dots in the middle. Now, it turns out this is true for any nice shape.
Nice shape.
Like a square.
It'll work for a square. Maybe we can do one last video with a square so you can see. Okay. As long as the shape doesn't intersect itself.
What if it does have to be convex?
Yeah, convex.
So, like...
Well, actually, you know what? I'm not 100% sure if it has to be convex or not. I'll check. Okay, I'm not 100% sure. But it definitely can't be self-intersecting. But this is a very handy way, Pick's theorem. And this, by the way, wasn't proved. The Greeks didn't know about this, I don't think, anyway. I don't think this Pick's theorem was proved until around 1900.
Cool.
So it's a difficult proof, but we're seeing the basics of it here. And let's take one last look at a square or quadrilateral, okay?
Alright.